My power over Ethernet room sensor prototypes just arrived and we're powering them up for the very first time. Will they work perfectly or fail spectacularly? Let's find out if my design choices paid off or if I've got some troubleshooting ahead. The goal for this video is to test 5 features of what I call the sensor core. The first one is a speaker, the second one is an infrared emitter, the third one is a brand new movement sensor. We have a digital smoke detector interface and addressable RGB LEDs. And we will test all of that using ESPHome. As requested, this new revision also features a DC power input, and I will use that one to carefully power on these PCBs for the very first time. And there it is. Beauty! Alright, let's see if it powers on. Yo! I really hope it does. So here again the comparison. This is the new board and this is the older board. Yeah, I mean I attached some cables too, so it's not a fair comparison. This video is sponsored by JLC PCB. They provide easy, affordable and reliable PCB and PCBA solutions, empowering electronics engineers to develop projects efficiently. Ordering PCBs is effortless. Simply upload your Gerber files, get an instant quote and place your order in minutes. For this project, I opted for the PCBA service to save time and get professional quality results far superior to my DIY soldering. They are also remarkably affordable. You can get 1 to 8 layer PCBs for just $2 thanks to their efficient large-scale production that delivers unbeatable prices without compromising quality. Speaking of quality, their lead times are reliable because everything is produced in-house, ensuring quality stability with strict controls at every stage. They even share detailed production updates so you can track your order in real time. Their turnaround is lightning fast with PCB production completed in just 24 hours. Easy to use, affordable to make and reliable to trust. You can always count on JLC PCB. For your next project, don't miss their 6-layer PCB special. Get $30 off with the coupon in the description and enjoy top quality 6-layer PCBs for just $5. This includes 2 microns, electroless, nickel immersion gold finish and no engineering fees for via in pad. Now back to my project. This is the DCN and the ground. The idea is to use this Phoenix connectors here and they don't fit. Oh no! I just found the first issue. Okay, now that's a big problem. They don't fit. Oh no. Yep. Okay. It kind of fits, but needs to be redesigned. So this is not perfect, but I don't even have to solder it. It just stays in there. Pretty cool. I will write down a list of everything that needs to be improved. Phoenix footprint is wrong. DCN voltage, silk screen. Yeah, it's hard to get everything right. But these are minor issues. This will fit in like this. And how much voltage is required? The power supply is obviously designed for PoE voltage. So around 50 volts, I think. So let's start with 24. 24 is always a nice value. And yeah, current, I would say, yeah, 200 milliamps should be fine. Okay. And then let's pray that it works. That's good, but also bad. It's not enough current. And I will now connect my multimeter to ground like this, because this way I can just measure with one hand. So now I can take a look at the voltage. Let's follow the voltage. We have DC voltage right here. Okay. No, we don't. There is no voltage right here. That's a problem. Maybe a problem of this connector here. So let's stop. Okay, here we have a connection. And here we don't have a connection. So this is weird. There is no contact inside of this connector. Let's remove it and use that one. This one actually has contacts inside, which we normally expect. And we power it on again. We have current flow and we can now start measuring voltages. That's not 3.3, that's a little bit less than 3.3. So let me use the thermal camera, because then we see if we have a big problem somewhere. Nothing gets super hot. The first voltage that we have is this V input here. 23.3, not too bad, because we have this diode here. That is a reverse polarity protection. If you wire it wrong, nothing will die, it will just not work. But maybe it doesn't have to die, maybe it's already dead. Let's see. Okay, we have this voltage here. It generates 5 volts. This right here is our 5 volts output. And so if I go here, it's 5.5 volts. It's actually a little bit much. We also have 12 volts here, generated by this LDO. This is used for the smoke detector, if you want to. And so the problem might be located here, because this thing creates 3.3 volts. And our 3.3 volts rail is a little bit low, 1.26. That's not enough. So now we have multiple possible issues. One possible issue would be that too much current is flowing on the 3.3 volt rail, which is not the case because we have very little current flow right now. One reason might be that I selected the wrong resistors. Feedback reference voltage should be 0.6 volts. Let me double check that. It's a little bit high today. So this voltage is too high, which means that the regulator regulates down. Now if this voltage is too high, then maybe it means that this resistor is too small or this resistor is too big. Let me turn off and let's measure this resistor here. Maybe I selected the wrong one. Yeah, this is R30. This is probably fine, but this is slowly creeping up. Looks like a capacitor is charging. It has 22.4 written on it, so I would assume that it's 220 kilo ohms, which it should be. Why is the voltage so high? I will now remove this DC-DC converter completely from the board, and then I will inject 3.3 volts, and then I will measure the feedback pin, because that would give me a clear indication that the DC-DC converter has an issue. Maybe the part is broken, who knows. I will inject it right here. Let's turn it on. Okay, it's not much current flow, 20 milliamps. And if we go here, we have 0.6. To me it looks like this DC-DC converter is broken. So I will harvest it from my old board, which is broken anyway. Okay, so let's turn it on again. Still no voltage here. Here we should have 5 volts. 5.5 volts. The maximum allowed input voltage is 5.5 volts, so it's a little bit high here. Maybe we can reduce the input voltage. If we add this resistor here, on top of R38, we should get less voltage, which means more voltage on the feedback line, which means the output voltage should reduce. So let's see, this should reduce to 5 volts. Oh yes, 5.1 is more reasonable. It doesn't help the DC-DC converter, unfortunately. So what is going on here? How is this possible? Pin 5 is the feedback pin. Pin 1 is the enable pin. Pin 4 is the input voltage. Pin 2 is ground. How is this possible? This is horrible. I have no ground connection. Oh my god. Yeah. So the good news is it's an easy fix. And the DC-DC converter is not to blame. I don't understand why the design rule check doesn't find this. Maybe I ignored the test. Interesting. Okay. Let's hope that that's the only connection missing. Zero output voltage. Yeah. I'm a bit worried that it's toast now. The DC-DC converter. Maybe I killed it. It's absolutely possible. And unfortunately I already toasted my second DC-DC converter too. Ay, 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 ay. Let's try the next PCB then. So lots of problems today, but we're getting there. We're getting there. Okay, so first, let's connect the ground connection before we power it on. Same issue here. Who would have thought that? Let's see if it works now. Oh. Oh. Incredible. Okay. We finally have our voltage here. That's amazing. I will double check all of the voltages. We have 12 volts, 3.3 volts, and we have 5.5. Yeah, the 5.5 needs to be fixed on that board. Let's actually add something a little bit smaller. Maybe let's use 270. 270. Voltage is off. Very nice. And now we have 5.02. That's perfect. All of the voltages are there. So let's program this. Okay, so I will use this FTDI chip to program my ESP32. So this is the connector here. What we need is RXT and TXT, and this will be connected to my MacBook. This is, by the way, 3.3 volts. That's important, otherwise you might damage your board. Let's connect ground first. Ground is right here. The receiver of my MacBook will be connected to the transmitter of this board. The transmitter of the MacBook will be connected to the receiver of my board. And then one last thing that I need to do is, actually two last things. I need to connect GPIO 0 to ground. And then reset the whole thing by connecting ESP enable to ground. And I'm running out of grounds, so I will use this ground here and then just use my tweezer here. So I prepared a config file for ESPHome. It will also enable Ethernet, which we didn't test, but also enable all of the features that I would like to test. Let's upload it using a USB. Maybe let's run. We have to compile it first, and now we can upload it. Oh yeah, we have no external power. Let's turn on the power. And now let's connect ground. Let's reset. And then we try to upload again. Yes, it's live and we're writing to the flash. So we successfully uploaded the program, but we have no idea if the Ethernet works. And right now we need a serial connection to program it. So I could now add the Ethernet jack and hope for the best. First turn off the power, of course. I will remove the external power and try to power it using my Ethernet cable. What could go wrong? I think I will use my thermal camera once again. Okay, it's getting warm, that's a good sign. It gets power over Ethernet. We can now try to ping it. So let's ping the IP address. Yes! Okay, the ping works. There should be a web server. If we go to Safari, yes, we have the web server. And the motion detector detects motion. It seems to work. That's very nice. We also have our speaker. I can change the frequency. Oh my god. Okay. And fire sensor is off. Motion sensor is off. So if we trigger a fire sensor, this is the fire sensor, fire alarm works too. And if I want to, I should be able to reprogram it using ESPHome over the network. So let's upload the sketch over the air. And OTA was successful. Let's try it again. Over the air. I love ESPHome. It's so cool. It's so cool. Okay, that looks amazing. One last thing that I would like to test is the LEDs. NeoPixel Bus doesn't work with ESP-IDF. For clockless lights, you can use ESP-RTM LED strip. Maybe I would like to use that. So let's use that then instead. I will add it to my config. Light. It is connected to GPIO 4 and the number of LEDs is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12. Let's just give it a try. Upload, no, run. I want to run it. Oh, okay. That looks good. I have my light, but I'm not able to turn it off. It's just turned on, full brightness. Interesting. Okay. I will just try this. Oh, no, not 60. I have 12. Stop this and try it again. Oh yes. Okay, that is amazing. So I can control the lights now. But I would like to use RGB. Yes, this is amazing. I could control the light, but not the RGB, just white. How can I use RGB? Okay, so I guess I have to trigger some actions. That looks interesting. So, switch, platform, template, ID, red light, name, red light, optimistic. Yes, we are optimistic. I'm very optimistic that this works. Turn on action. And we also need turn off action. So my turn off action will turn it off. Let's put it back to 0 and run. My light. Yeah, there is no my light. So I guess I have to give it an ID of my light. Red light. Oh, this is amazing. One thing that we didn't try is the infrared LEDs. I have this light, and this one can be controlled using infrared LEDs. You can put them everywhere and then control it with this PCB. First we need to add some code. I have it in my living room. I have all these codes here. Portable lamp power on. Yes, that's what I'm... It's a button. Good. I already prepared these codes here, and now I should get new features. Portable lamp on and portable lamp off. Isn't that cool? Portable lamp on, portable lamp off. That's it for this video. I'm currently working on the enclosure and also on some sensors. So my plan is that this is the sensor core, and you can then add additional functionality using these pin heads. So just to give you an example, one thing that you might insert here is this millimeter wave sensor. And it actually has its spot right here. So this is where it belongs. And I will test this in another video. And I will also show you some additional PCBs that you can mount here, because this way I keep the price of the core PCB as low as possible while making it extensible. So if you need CO2 sensors, you can add them. If you need temperature sensors, you can add them. And if you need infrared receivers, not just transmitters, you can add them. If you need a microphone, you can add it. If you need an infrared matrix sensor, which is very expensive, you can add it. This is the plan. And so far it looks pretty good. I'm also very happy with the quality of this PCB. I'm also working hard behind the scenes on making this board available to you. So if you are interested, head over to playduino.com/sensor and sign up to my email list. If this video was helpful, please like and subscribe to this channel. Thank you so much for your feedback. I'm curious, what are your thoughts? Let me know in the comments. And if you haven't already, please check out my playlist on this project, because I've been working on this for quite a while now and it's about time to finish this project. See you in the next video.